In our first video from section 9.2, we just dealt with the difference between linear functions and exponential functions. And again, the idea was that with linear functions, you're always adding or really subtracting, right? Because subtraction is just addition of the opposite. So you're really always adding to get from one successive output to the next. Whereas with exponential functions, you're actually multiplying to get from successive output to successive output. All right, so from one output to the next. All right, so now here we just get into the general form for an exponential function. Okay, so exponential functions, the general form is going to be this: f of x equals c times a to the x, where c is going to be a positive number for our purposes. I mean, could c be a negative number in future classes that you're in? Yeah, but for our purposes in intermediate algebra, c is going to be a positive number, and a is also a positive number other than 1. Okay, so what ends up happening here is the point 0 comma c ends up being the y-intercept, right? The vertical intercept or the y-intercept, and it's pretty clear to see why this can how this happens, because what is the y-intercept, right? The y-intercept is the point where x equals 0. So if I would do f of 0, what do I end up with? I end up having c times a to the 0, right? But if you recall from exponent properties, any non-zero number to the 0 power is going to equal 1. So a to the 0 is 1, so this is really just c times 1, which is just c, right? So f of 0 is going to equal c, and that's why 0c is the y-intercept. Okay, so that's pretty easy to see. So the value of c is always the y-intercept. Now, the a value determines whether the function is going to be exponential growth or exponential decay, and that's what we'll get into now. Okay, so when the a value is greater than 1, right, because remember, it has to be positive and it can't be 1. So when it's greater than 1, the function is known as an exponential growth function, meaning it's increasing. It's an increasing function. And that a value we're going to refer to as the growth factor. Now, just in general, you can always refer to a, if you want to, as the base. But more specifically, when a is greater than 1, it's known as a growth factor. Okay? But really, just more generally, a is always just a base, whether it's greater than 1 or less than 1. So when it's greater than 1, it's known as a growth factor, and we have an exponential growth function. So right here, I give you the graph of an exponential growth function, okay? Because you can see it's increasing as we go from left to right, and it passes through the point 0, 2. So 0, 2 is going to be your y-intercept, and then the next point on here is actually 1, 4, and then the next point on there is 2, 8. Right, the next integer point on there is 2, 8, and then the next one would be 3, 16. So if you recall what we did before in the last video with the successive outputs, we can do the same thing here. Here we went from 2 to 4 to 8 to 16. So to get from one successive output to the next, what we're doing is we're multiplying by 2, right? So in this case, the 2, which is our constant factor, is actually going to be our a value, right? Which is the growth factor. And of course, this point here, 0, 2, we said that that always gives us our c value. So c equals 2. So we can actually write the equation of this exponential function. If we call it f of x, we'll call it f of x. We'll say f of x equals, right, it's c times a to the x. And in this case, c is 2. And a is also 2. So it's 2 times 2 to the x. So that would be our That would be our function. Okay. Now, the important thing to see here is that this is not the same as 4 to the x, right? What a lot of people would do with this is they would say 2 times 2 gives me 4, and then this is the same as 4 to the x. It's not, right? Because just think of order of operations, right? Order of operations would tell you to do the exponent first, and then to multiply by the 2 out front, right? So 2 times 2 to the x is not the same as 4 to the x. So keep that in mind, right? This is not equal to 4 to the x, right? It's not equal to 4 to the x, right? Just keep that in mind. So we have the equation of this function here. Now the other thing that we've been doing throughout this course is we've been talking about domain and range, and it's fairly easy to see at least what the domain is from this picture, right? Remember with the domain, we just look from left to right. So this thing is actually going to go all the way to the left and all the way to the right. So the domain of this is just going to be all real numbers, which would be negative infinity to infinity, right? And again, it makes sense if you just look at the equation, right? Is there any bad thing that can happen here by plugging in any value for x? No. I mean, x can be, an exponent can be any value, right? It can be a positive number, it can be a negative number, it could be 0. So the domain is going to be all real numbers, negative infinity to infinity. Now the range is different because you can see here as you look to the left that this line is going down, but it's actually leveling off over here. And it looks like it's actually getting close to 0, but never quite reaching it, and that's actually what is happening there. The range of this function is actually going to be from 0 up to infinity, but it's never going to quite reach 0, so here we have a parenthesis. Okay? And because of the fact that it never quite reaches 0, that means we have what's known as a horizontal asymptote. If you remember, we did vertical asymptotes when we did rational functions. We might have briefly talked about horizontal asymptotes as well at that point, but we didn't really specifically define them. But this function here actually has a horizontal asymptote because y is getting very close to 0, but not quite reaching it. So the horizontal asymptote is actually going to be this line, y equals 0, right? This would be your horizontal asymptote because the graph is going to come very close to 0, but never quite reach it. All right? So the domain is all real numbers, the range is 0 to infinity, and then there's a horizontal asymptote at y equals 0. All right? So that would be an exponential growth function. And then the alternative situation is when we have the a value being less than 1, we call it a decay factor, right, as opposed to a growth factor, and the function is what's known as an exponential decay function, all right, which is a decreasing function, meaning that it goes down, right, it falls from left to right. So similar process we can do here as with the last one. Again, this is going up to infinity over here, and this is getting close to 0 over here. But we have some points here. 0, 3 is a point. This was negative 1, 6. And then this is negative 2, 12. So again, what we do is we say, how do you get from successive output to successive output? Well, from 12 to 6, and then from 6 to 3, you can say we divided by 2, but again, we want to always think of this as multiplication. So dividing by 2 is the same as multiplying by 1/2. So we're really multiplying by 1/2 here. So this 1/2, that's your a value, which in this case is your decay factor. And of course then, so 1/2 is a. The y-intercept, that's always going to be your c value, right, your y-intercept. So if we're going to write the equation of this function, it would be g of x equals c times a to the x, right? We're always using this as our general equation for an exponential function. And in this case, c would be 3, and a is 1/2. So it's 3 times 1/2 to the x. All right? So that would be our function. 3 times 1/2 to the x. Okay? And then again, this actually has the same characteristics as the other function, right? The growth function. The domain, it still goes all the way left to right, so it's going to be negative infinity to infinity. The range, since this also gets really close to 0 but never quite reaches it, the range is going to be 0 to infinity again. And then the horizontal asymptote will have again is going to be the line y equals 0, which again would be that line there, right? It's getting very close to that line as you go to the right, but it's never quite reaching it, all right? And we didn't do this with the last one, but you can see a simple example. I mean, just let's say what happens when x gets pretty big, like when x is even like, I don't know, 10. When x is 10, let's see what happens. What would g of 10 be? Right? So as you go a little bit further to the right, g of 10 would be 3 times 1/2 to the 10th power. And 1/2 to the 10th power is actually 1 over 1024. I believe it's 1024. Let's just check this real quick. What's 2 to the 10th? 2 to the 10th power, is it 1024? Yeah, it's 1024. So g of 10 in this case is really just 3 over 1024. So already the idea of this is that this is getting close to 0, right? 3 over 1024 is already pretty close to 0. And then when you get to 11 and 12 and 13 and even numbers bigger than that, you're going to get even closer to 0. So that's the idea. It's getting really, really close to 0, but never quite reaching 0. All right, so y equals 0 again is your horizontal asymptote. All right, and then just a basic evaluating question. If I just have this general function here, f of x equals 5 times 1/3 to the x, how would I find the y-intercept? I would pretty much just plug in 0, right? That's one way you could do it. Or you could just realize, hey, this is my general form for the exponential function, and I know my c value is 5. So the y-intercept is just the point 0.05, right? Because this was my c value. Right? So that one really requires no work. And then the other two require, like substituting. So f of 3 would mean you would plug in or substitute 3 for x. So you get 5 times 1 over 27, which is going to be 5/27, right, which is pretty small already. And then by the time you get to 5, right, because this is an exponential decay function, you would have 5 times 1/3 to the 5th, which is actually going to be 5 over 3 to the 5th, which is 243, right? Because 3 to the 4th is 81, and then 81 times 3 is going to be 243. So again, this is another one that would be exponential decay, because as you go to the right here, the values of y are getting closer to 0, right? Like if I did f of 10, it would be even smaller. It would be 5 over an even bigger number. If I did f of 100, it would be 5 over an even bigger number. So they're getting really, really close to 0. Okay? And now that we have this general process, what we could do is, if we want, we can go back to our tables from the beginning, and we can just write those functions as well, right? The first one that we had done, our constant factor was 4, so that was our growth factor, and our y-intercept was 8. So the equation of this function here, the second one, was just y equals 8 times the growth factor, which is 4, to the x power. Right? So this was our c value, and this was our a value. And then I can go to the fourth table, and I can again see, well, there's my y-intercept, and here's my decay factor. So my 40 in this case is going to be c, and my 1/2 is going to be a. So the equation of this one would have just been c, which is 40, times a, which is 1/2 to the x. Okay? So that's just finishing up the tables that we had done in the previous video. So we got one more video on this. It'll be involving compound interest.